So we've been looking at regression analysis. We've been seeing it one variable at a time. We've seen the effect in a positive direction. For example, sales being regressed on advertising. Sales is the Y, advertising is the X. We've seen a positive slope. We've also seen a negative slope with respect to, say, sales regressed on price. These reflect positive and negative correlations. But it also tells you that the relationship of sales to all my input variables, captured as a matrix that I'm calling X, can get complicated. And it could be the case that I will need to look at multiple variables together to see the full impact. That is what multiple linear regression is about. So let's start building a multiple linear regression model. And let's start maybe with the simplest case of just two X's. And the two X's that we'll look at are advertising expenditure and discount percentage. Taken together, we're going to call these variables independent variables 4. They're going to impact sales, but they're going to impact it together. And the way independent variables are now specified is both variables are being carried. So I'm going to have an X matrix that's going to have two columns going into the analysis. But here's the interesting part. Other than just that is setting two variables inside my independent variable vector or my independent variable array, there's nothing else that needs to change in the modeling exercise. The rest will remain exactly the same. Let's observe. So now I've specified my independent variables, which are two variables, not one. I'm building my fourth regression model. My first three were simple regression models. That's why we're calling this regression model 4. I'm again instantiating or creating an instance of linear regression, same way as before. And I'm again taking X train and Y train in order to fit. So the method is again fit, X train and Y train. And because of this trick that I'm using to create the independent variables up front, I'm still taking that entire independent variables 4 inside my X train, exactly as I'd done before. So once this has been done, this has now been fit. Here comes a little bit of a problem. How do I see the output of this? We can, of course, and we're just going to do that, see the coefficients. The coefficients will now be an intercept and two slope coefficients. One for each of the X's going into the model. One for advertising and one for discount percentage. In that order, because that's the order in which they entered my X matrix or my X train matrix that went into fit. So now when I ask for coefficient and intercept, let's see what happens. Coefficient is now going to give me a vector. Previously, it also gave me a vector, but with only one element in it. Now it's going to give me a vector with 28 and with minus 1.8. My intercept is 6.43. To plot this, I'll need to be a little careful. But instead of manually entering advertising expenditure or discount percentage, I can do certain things. Observe. What I can print is I can print the first coefficient. Remember, Python begins with 0 as it indexes. So the first coefficient and multiply it with independent variable x4 0. And when I do this, when I see this, it is going to pick up advertising expenditure as the name of the variable. So I don't need to track what 0 corresponds to, so long as I can track the index. This is just to write the equation down. But when I write this equation down, I can now write it as a coefficient for expenditure, advertising expenditure, and a coefficient for discount percentage. Now, this is an interesting output that I get Because if I go up and I look at discount percentages from my simple linear regression, let's look at this. This was my discount percentage equation for my simple linear regression. Sales on the Y, discount percentage on the X, and a positive slope. This was my equation. This is my equation. However, let's see what this looks like in my multiple linear regression equation. In my multiple linear regression equation, this turned out to be a negative coefficient. What this means is that the effective discount percentage on sales is moderated by advertising. It means that if I fix advertising and I now increase discount percentages, I should not expect an increase in sales. In fact, I might see a small decrease in sales, but this might be an insignificant decrease. So the discount percentage is in some way tied into advertising expenditure. Together they have an effect. And the previous positive effect that I saw on discount could be picking up things in advertising as well. It could be the case that the lift that I was seeing due to discount was due to a parallel lift that was also happening in advertising. Why do I believe this to be the case? From a business perspective, and we're not really talking in business terms here fully, from a business perspective, it could be because a discount is also an advertisement. And a funding mechanism for discount, a way to promote that discount, is accounted for in advertising expenditure. So the effectiveness of a discount depends on advertising as well. The two X's are related to each other. And this is where multiple regression becomes very important. Because if the input variables are related to each other in these ways, the simple linear regression may not simply collectively tell you what the multiple linear regression is. The presence of two related variables change in very unexpected ways often the way they together impact the output, which is sales. This is why supervised learning is interesting, and this is why supervised learning sometimes becomes a little difficult. It is not the same as looking at all the inputs one at a time. Let's play this a little further, and let's look at what happens if I now include product price, which we had seen as a correlation in the opposite direction. You know what's going to happen now. You've seen this happen now a number of times. We're going to look at multiple linear regression now with 3 X's. But using the way that we have set up the code and the workflow that we are doing, all I need to do is to set my independent variable vector well. Now, what is this independent variable vector doing? By the way, I should have emphasized this before and I did not, but let me emphasize it now. When I say this variable, when I create this, I am not creating the variable itself. What I am creating is its name. When I create the name and I pass that name into XTrain, it reads the name vectors and therefore equivalently picks up advertising expenditure, discount percentage, and product price. I should have emphasized that, because what it allows me to do is to now pass any number of names that I want to inside here. And now I'm going to pass 3 separate names. And therefore, when I put this into X, 3 separate variables. So just to be clear, when I set up my variables this way, I'm actually setting up the names of the variables. When they go into the data frame, they then become the variables themselves. So now I've got advertising expenditure, discount percentage, and product price. You now know exactly what I'm going to do. I'm going to run instantiate within the training data set, take all these 3 variables, or more precisely, all these 3 variable names, and therefore the variables associated with those names, 3 X's now, and 1 Y. This is now run. I can print it again, just print the coefficient. If I'm printing the coefficients as a vector, I do not need to specify how many coefficients. because within my fit, it already knows how many coefficients will be there. So as soon as I say dot coefs, I'm already calling for 3 coefficients, and those 3 coefficients will come as a vector. My intercept will come as a number. So I have the vector and I have the number. I can print it again. Remember that the independent variable is tracking the name. So 0 is the first name, 1 is the second name, and 2 is the third name. And I can multiply that together with the coefficients with the same indexing, so that my coefficients and my variable names get locked to each other. And here is my equation. I have a coefficient for advertising expenditure, a coefficient for discount percentage, and a coefficient for price. The coefficient for price remains the same, minus 8.4. What does this minus 8.4 mean? It means that if there is no change in advertising expenditure and no change in discount percentages, 1 unit increase in product price can be expected to lead to an 8.4 unit decrease in sales. Similarly, if advertising and discount are held fixed, 1 unit decrease in product price can be expected to lead to 8.45 units increase in sales. But please remember that interpretation. If you are reading numbers like this from multiple linear regression, interpret them as holding the other variables fixed, so that their coefficients do not enter into the output prediction. They are not changing. So here, no surprises with respect to product price. It was negatively correlated. Even with advertising and discount percentages, it remains negatively associated with price. I can keep building this out, but I'll need to be a little careful with variables that are of a different